Hello everybody and welcome back to my YouTube channel. I am Varshini from Sri Venkateshwara College of Engineering and I am currently pursuing my data science engineering. Today's subject is data structures and our topic for today will be sparse matrix in image compression. Introduction to image compression. Image compression is the process of reducing the file size of an image while maintaining the acceptable level of quality. Importance is it is used to optimize the storage, reduce transmission time, and improve efficiency in data storage systems. Methods of image compression is lossy and lossless. We will look into it later. And connection to data structures is that when we have to compress an image efficiently, we use different types of data sets and to maintain this large amount of data, and usually we use a sparse matrix to optimize the storage for these images. We have a simple block diagram of how the compression works. The original data is compressed using the encoder, and then the compressed data is decoded using the decompressor, and this is basically how this whole system works. So JPG compression is a standard image format that uses lossy compression. The image is divided into blocks and the discrete cosine transformation is applied to each block. It is a certain process that is applied to each block of the image that is split up. The whole image is divided into smaller blocks and each block is applied the DCT protocol, and then the result will be a sparse matrix which most of the elements are either zero or coefficients of it. So what is a sparse matrix? A sparse matrix is a matrix where most of the elements are either zero or have negligible values. If you look at it in simpler words, the number of non-zero values are less than the number of zero values in a sparse matrix. So we have an example of a sparse matrix. As we can see, this is a classic 5 cross 5 matrix, but it has so many zero elements and the number of non-zero elements are so less compared to the zero elements. We have about 25 elements in this matrix and about 4 of them are non-zero elements. So when we try to store matrices like this in our system, it takes up the memory of almost 25 elements. That is, all these zero elements, the 21 extra elements are also given allotted spaces in our system. To avoid this, and this takes up large amount of data space, the memory spaces. So this can lead in wastage of available space for the zero elements which have no significance into the matrix. So this matrix has so many zeros, and using the sparse matrix representation will only store the non-zero values as I have discussed earlier. The contrast with the dense matrix. The dense matrix contains high proportion of non-zero elements. As we have discussed, the number of non-zero elements are greater and will be in wasting of the storage space. Importance in computation. Storing only non-zero elements saves spaces and computation time. When we are trying to execute this matrix or any application or like any operation on this matrix, we will notice that all these zero elements to be processed, all any addition, multiplication programs that are being performed on this matrix will waste so much of time trying to compile all these zero values and will still have no significance into the actual answer. Data structures for sparse matrix. How is our subject actually related with the concept of sparse matrix? Memory efficiency. In this topic, we see that the sparse matrix not only stores non-zero elements in their indices, significantly reducing memory usage, as I have told earlier, compared to the dense matrices. Even zero elements are stored, leading to waste space, and most of the elements are zero. By storing only the non-zero elements, sparse matrices are so much more memory efficient. This is like the main motto behind usage of sparse matrices, which is why it is being stressed out so many times. The next topic is faster computation. As we just looked at a glimpse before, since sparse matrices mostly contain zero elements, like operations like multiplication and additions can be optimized. Algorithms take advantage of the sparsity, that is skipping the zero elements, that can reduce the number of computations, making these operations faster compared to the dense matrices. As we saw in the previous example, there were around 21 zero elements. So when the compiler tries to multiply that matrix with anything, it would have to perform generally, like for a normal matrix, it would perform 25 operations. But because this is a sparse matrix which contains so many zero elements, only the 4 elements that were non-zero will be computed. So obviously multiplying 4 digits will take lot less time and effort compared to multiplying 25 digits even for the computer. We have the concept of efficient storage representation. In this representation, we use specialized data structures to store them as either in a compressed sparse row format or in a compressed sparse column format. These formats only store the non-zero elements along with their rows and column indices, which make it easier for accessing the element and the retrieval of non-zero elements without needing to iterate through all the elements of the matrix. If we want to access a certain element that is in the fourth row, third column of a given matrix, we wouldn't have to read all the data or traverse through all the elements of the matrix when we know that exact location of this element in the matrix. This way, storage representation is more efficient and easier to access. Reduced computational overhead means in the sparse matrix computation, most operations like matrix vector multiplication or solving system of linear equations can be optimized by skipping the zero or non-zero values. Such operations usually take a lot of time in general, but when we have a lot of zero values, we are using all that time in calculating and it will end up in a value that is also not significant to us. So in such cases, we can reduce unnecessary processing leading to computational overhead, especially with large matrix and high sparsity. The scalability of large matrix. Sparse matrices are particularly useful in problems involving large-scale data such as machine learning or scientific computation. These both fields deal with large amount of data that are larger in number and in size. These two problems often involve machines with zero and use sparse matrix representation allows them to scale efficiently without running into memory or performance issues. Storing unnecessary zero values will lead in slower performance of the computer also, and running it in the memory will lead to waste of space and also waste of time. These can be avoided using a sparse matrix. How sparse matrices apply to image compression. Sparse matrices can help store only non-zero pixel values, which are often only the relevant parts of the image. And exploiting sparsity, instead of storing every pixel value, we store the only non-zero or significant values to reduce the file size. Grayscale images is a concept that we use in this case. We have an example of a grayscale image. We have a girl laying down. That is a grayscale image. It is simply like a black and white image where most of the pixels are black values, that is equal to 0, and except some values that are non-zero where the actual object actually resides. So, instead of storing each pixel, the sparse matrix stores the position and values of the non-black pixels. As we can see in this particular picture, a majority of the picture, almost about 40 to 50% of the image is just plain black. So, there is no point in storing all these black values in the sparse matrices. So, for image compression, only the parts of the skin that is showing and partial parts of her hair, the values of those pixels are stored in a sparse matrix. So when we are trying to access the image, there is not much loss in quality, but the size of the image has drastically reduced by around 40 to 50%. Sparse matrices and lossless image compression. In this case, we have two types of image compressions as we saw earlier, which is lossy and lossless compression. Lossy images are usually bad quality images that we get after compression. But lossless image compression tries to retain the maximum quality of the image by trying to just reduce the image size in a efficient way. Compression where no data is lost and the original image can be perfectly reconstructed is called a lossless image compression. So when we try to develop the compressed image, we can get the perfect image of that we had compressed before. So JPG compression, after applying the DCT to an image, the resulting matrix often has small values close to 0. These values are discarded in JPG and only significant values are kept, resulting in sparse matrix is encoded to save space. Here we have a pictorial representation of how the captured image will be, like used to decode and encode these data. Challenges and limitations in this case. As we can see, this image, we can make out that this image is a tree, but is this image of a good quality? No, because it's very pixelated and it looks very shabby. So complexity is a sparse matrix algorithm can be complex to implement. These compression and decompression algorithms, the encoder decoder algorithms that we saw before, can be very complex and can be very time consuming and memory efficient to be run or to be constructed in the first place. The overhead, some sparse matrix operations like random access can be slower with denser matrices. Image complexity. Sparse matrices work best for simple images with uniform areas. Now, as we can see, as we saw in the picture of the girl previously, the image was very simple and small and very not so complicated, so it was easier to compress images like that. But with images that have different textures and different layers and a lot of variation in light and in colors would also make it very difficult to implement these complex algorithm on pictures like that, leading to lossy compressions that make the pictures look shabby. For a high detail image, like for example a forest, the sparse matrix representation may not offer significant advantages as most elements will be non-zero, making the sparse matrix approach less effective. Like for example, if we have the number of zero elements less than the number of non-zero elements, there is no point in implementing the sparse matrix concept because most of the elements will still be traversed when we are implementing the sparse matrix. So this makes it less efficient. After discussing the pros and cons of image compression using the concept of sparse matrix, we have reached the end of this video. I would like to thank you all for watching the video. Thank you.